Alright, this is 3.2, identifying linear functions. Your objective today that you can identify linear functions. Some terms to know. The first one is linear functions. What a linear function is it's pretty self-explanatory almost in that it makes a straight line. So a linear function should make a straight line. And in comparison, a nonlinear function does not make a straight line. A straight line. A lot of times you might think of this as being curved. A solution of a linear equation in two variables is going to be given as x and y. And that's the x and y on a given line. A discrete domain, you can kind of just more simply think of this as being dots. So a discrete domain is going to be dots instead of a continuous domain where everything is connected. You'll kind of see an example of this as we go. Connected, there we go. And I kind of a lot of times think of this also as, well, a line. So a couple core concepts. So in words, an output is 3 more than the input. The equation for that is y equals x plus 3. Making an input-output table, you would have an input of -1, your output is 2, because -1 plus 3 is 2. If your input was 0, your output is 3. You can see we're just adding 3 onto what our input is. The mapping diagram we'll go over a little bit more is -1 goes to 2, 0 goes to 3, 1 goes to 4, and this actually is a pretty interesting concept, this mapping diagram, and it actually can really help you out. Finally, we have the graph. The graph goes kind of going up and to the right. You'll notice that we're only going up by 1 each time, and that's because of something else. Discrete domain is a set of input values that consists only of certain numbers in an interval. Example, integers from 1 to 5. So an integer, if you remember right, is a whole number. And so we can't include decimals in that. So whenever we do integers going from 1 to 5, so 1, 2, 3, 4, and 5, our integers are only 1, 2, 3, 4, and 5. In this case, our domain, that little curly bracket, is 1, 2, 3, 4, and 5. The next one that we have is a continuous domain, and this was a discrete. A continuous domain is something like all numbers from 1 to 5. And so with that, if I have that same graph, and I go 5, 4, 3, 2, 1, and I do my little tags up here, all numbers from 1 to 5, I start at 1, filled in dot you'll notice, and I'm going all the way to 5 with another filled in or closed dot. In this, our domain, with the little curly brackets, is 1 is less than or equal to, because we can be at 1, x, and that is less than or equal to 5. And that's our domain. Again, the big idea is list them from smallest to largest and make sure we have no repeats. A couple of examples. So in example 1 and 2, determine whether the graph represents a linear or non-linear function. So if we're looking at a graph, and it kind of, let me do a different color so we can kind of see the start. It kind of goes like this, and then it kind of curves. You can probably make a guess on this one that this one is non-linear. It's curved. And you'll cover what that kind of line is at a later point in time. You don't really have to know what type of line that is right now. Curved, there we go. Alternatively, if I have something like this, and you'll have to forgive my drawing, it's not going to be the straightest thing in the world. But if I have something that goes off in a straight line, assume that's straight. I'll put a little thing, straight. If I have a straight line, this is going to be linear because it is straight. In examples 3 and 4, determine whether the table represents a linear or nonlinear function. Explain. And so the way to determine a linear or nonlinear function when giving a table is we're looking for a pattern, and really a specific pattern. And so let's look at this first one. This first one, we go from -1 to 2 on the x's. So I go -1, 0, 1, 2. Now on the y's, I go 0, -1, 0, 3. And as I read through these, I go, okay, on my x's, I go +1, my x, I go +1, my x, I go +1. All right, there's a little bit of a pattern there. And then on my y, I go from 0 to 1, and that's -1. And then from -1 to 0, that's a +1. And then a 0 to 3, that's a +3. In this case, this is not linear. This is nonlinear. Nonlinear. There is no pattern. And specifically, the pattern should be a constant kind of change. It shouldn't be. It should be kind of addition-based, not. It should be addition-based or subtraction-based, not multiplication. So, if we have another one, we're going to go from 1 to 4. So x, y, and I'm going to go 1, 2, 3, and 4. And we're going to do -1, 2, 5, and 8. And so I say, okay, this one, I'm always going to start with my x's. Make sure I'm going by the same amount each time. So add, or +1, +1, +1. All right, cool. All right, to go from -1 to 2, I have to add 3. To go from 2 to 5, I have to add 3. To go from 5 to 8, I have to add 3. So in this case, this is linear. We have what's called a constant slope. And in this case, it winds up being 3 over 1. Oops, not 4. 3 over 1. I want that other eraser back now. 3 over 1. And you'll notice this is the y and this is the x. All right. In examples 5 and 6, determine whether the equation represents a linear or nonlinear function. Explain. So in number 5, we have y equals 3 minus 2x. And in looking at this, what we can see is that there's only the x, and the x specifically doesn't have anything up here in the exponent location. And so the exponent is by itself. And so what that tells us is that this is linear. A linear equation is going to have an x where the exponent is 1. And most of the time we don't write the 1 there, so if there's nothing with that x in the exponent place, it's going to be linear. So exponent equals 1. All right, let's look at number 6. Number 6 says y equals -3 over 4x to the third. And kind of again, what we're looking for is right here. And what we see is this doesn't have a 1, so this is going to be nonlinear. The exponent equals 3. Let's do another version of this. In this one, it says, in examples 7 and 8, find the domain of the function represented by the graph. Determine whether the domain is discrete or continuous. So slightly different from what we've been doing prior to this. So if I look at this, and I kind of set this up, this goes up to 6. 1, 2, 3, 4, 5, 6. Awesome. It goes over 1. That's where it starts. Looks like we're going down and we end at 5. 1, 2, 3, 4, 5. And up 1. And let's see here. Yeah, okay. And this is a super straight line in case, actually that was a pretty decent line for me. Alright, so this is at 5, this is at 1, this is at 6, this is at 1. And so we need to determine the domain. So I'm going to put down domain. I know I'm going to have my little curly bracket. And what I notice about this is that this is a line. And we talked about this in the last unit, where what this means is, or not last unit, last lesson, where what this means is my domain starts where the line starts, and so in this case it starts at 1. And then I'm going to move to the right, and because this is a continuous line, I don't really stop, so I'm going to use this less than or equals to sign with an X. I'm going to say that's less than or equals to where the line stops. In this case, the line stops at 5. Now, you could kind of continue on and be like, oh, the range is this, and that's kind of good practice, but it doesn't ask us for that. And so what it asks us, though, is this discrete or is this continuous? In this case, it's continuous. It's all connected. And that's the reason why, is it's all connected. It's not individual points. Let's look at number 8. It's up at 3. 1, 2, 3, and over 1. Alright, now again, it's going to ask us the domain. This is 1, this is 2, this is 3. This is 1, 2, 3, 4, and 5. So our domain, in this case, is, again, it's all of the x values, but each one is separate, and so it's 1, 2, and 3. The range, oops, I don't need the range. I was getting ahead of myself. I don't actually need the range. What I need to determine is if the domain is discrete or continuous. In this case, it is discrete. And we can tell because these are just a bunch of dots. They're not connected. And that finishes up 3.2. Check with your teacher on what your assignment is. Have a good one.